Welcome to the first instructional video for week 4 of quarantine chemistry. This week, we're going to focus on what happens when we start to allow the amount of gas to change. Everything we've studied to this point, there's only been a certain amount of gas in a balloon and a sample. So we haven't had N or molar amount in any of our equations or our laws so far. So this week, we want to figure out how does changing amount impact pressure and volume. Then we're going to look at this interesting phenomenon where no matter what pressure, volume, temperature, and amount combination you put together, if you have a specific gas, so let's say air or carbon dioxide, if you have that specific gas, no matter what PV, N, and T you plug into that calculation down here, this PV over NT, you always get the same answer. We're going to finish up this video by talking about what we call standard molar volume and then standard conditions. So how does allowing moles of gas to change affect the pressure and volume? Notice we didn't say anything about temperature because amount and temperature really don't have a direct interaction. So adding air to a balloon doesn't change the temperature of the balloon, or changing the temperature doesn't necessarily change the amount. So we're going to assume that for the simulations that we do, we're going to hold temperature constant for them. All right. So is the relationship between pressure and amount inverse or direct when V and T are constant? Think about this for a second. If you take an aerosol can, so let's say a paint can. At the beginning, the pressure is really, really, really high. As you go through and you use that spray can to paint something, when you get down to the end of that paint, how low is the pressure? So as you remove gas from inside that can, N goes down, what happens to the pressure? It goes down as well. Well, let's take a look at a simulation. So for the simulation, we're going to hold volume constant. We're going to look at how many particles we put in, and then we're going to fill in our little table over here. So P is pressure, N is amount, and then we have our K value. That's just the value of P divided by N. And what we should see is that, one, they're constant, but we should also see that as the amount of gas goes up, look what happens to our pressure. If we let this stabilize and we look at the high and low numbers as this pressure fluctuates, what we'll see is we end up with a pressure for 50 particles. Our pressure ends up being 5.85 units of pressure. In this case, it would be our atmospheres. If we change that and we put another pump of gas in and we hold the volume constant, you notice temperature is not going to change either. So volume and temperature are constant. Notice the pressure went up, went from about 5.8 to now we're around 12. Again, let this thing stabilize, do the high-low divided by 2, basically find your average pressure. It ends up becoming 11.7. When we have 100 particles, and look what happens. We get that 0.117. So P over N is constant. P over N is constant. But notice what happens. As we increase the number of particles, as N goes up, P goes up. So what does that tell us about our relationship? That tells us that it is directly proportional. So based on the simulation, when volume and temperature are constant, pressure is directly proportional. That means when we add more gas to the container that is unable to expand, the pressure goes up. Okay. Well, now let's take a look at what about volume and amount? volume and amount. How are they related, inverse or direct, when pressure and temperature are constant? So now this is like blowing air into a balloon. So when the amount of air you put into a balloon increases, you put another breath of air into a balloon, what happens to the volume? It expands. So more air into the balloon, what we see is we get a greater volume. More air in, bigger balloon. All right, so now we're going to take a look at the relationship between volume and amount when temperature and pressure are constant. So to start, we want to see the width. The width is going to correlate to volume. So the wider it is, the more volume it has. If we shrink this down, the volume is going to go down. If we expand this out, volume goes up. But look what happens. We're going to start off with one full pump of our gas. We're going to hold pressure constant and allow the volume to change. So that's going to hold at 5.8 atmospheres, 300 K. We have a volume of 10 units. We have an amount equal to 50. What happens when we put more gas in? So let's go up to 60 particles. At 60 particles, we have a volume of 12 units. What happens if we go up to 70 units? We have a volume of 14.2. What we see is as the amount increases, the volume increases when pressure is constant. This is equivalent to putting air into a balloon. Every breath you blow into the balloon gets bigger. The volume increases when you increase the amount. So that's our relationship that we see for our volume and amount. It's direct. So volume and amount are direct. Pressure and amount are direct. What does this show us about P, V, N, and T altogether? We're going to take a look at a gas sample made of one kind of gas. So we'll see in the simulation, we have one colored little dot, one gas. We're going to take a look at how any combination, doesn't matter what pressure, volume, amount, temperature, we're always going to end up with a constant amount, a constant value. So the simulation, if we take a look at this, we're going to reset it. We want to count the particles, okay? We want to look at the width, and we're really not going to hold much of anything constant, okay? Let's take a look at one pump of gas, 50 units. Pressure is around 5.85. The volume is 10 units. We have 50 particles. And for all intents and purposes, what we're going to see is everything's just going to be at a constant temperature. We'll do this. Last one, we'll change the temperature. So let's see what happens to this 0.0039. This is P times V divided by N times T. So this K over here is PV over NT. P times V divided by N and T together. Let's say we put a volume, let's change this and make this go down to 5. So we just cut the volume in half. Volume went down to 5. My pressure averages out to be about 11.7. My particles are still 50 and my temperature is 300. We get the exact same product. PV over NT gives us that 0.0039 again. Let's go back to the original volume now. Let's go back to 10 units of volume. Let's add a second pump of gas in there. We're going to be at about 11.7. Our volume's back to 10. Our particles are now at 100, and our temperature is at 300. We get the same exact answer again. If we take P times V over N times T, we get that constant value again. Let's look at one more thing. Let's change our temperature. Let's increase our temperature up to, let's go to, see if we can stop right on 500 here. There we go. So we got 500 Kelvin. We've got 100 particles. We've got a volume of 10 units. And our pressure is going between, give us 19.5 for our average pressure. And look, again, we changed the temperature. We changed our amount. We changed our volume. This was our starting point. No matter what the combination of PV, N, and T are, we always get the same answer. And we look at this. It's going to lead us to a set of standard conditions and something called standard molar volume. So what we're looking at now is anytime we have a gas that's the same gas, it can be an element like argon. It can be a pure substance, just carbon dioxide. Doesn't matter what PV, N, and T are. If we put PV over NT, it's always going to equal a constant value, which means we can set one set of PV, NT values against another set of PV, NT values. So let's say we knew pressure, volume, amount, and temperature, and they gave us a different pressure, different volume, and a different molar amount. And they asked us to figure out, well, then what would the temperature be at those conditions? We would just be able to use that as our equation and rearrange for T2. Gases have a very unique property in that no matter what kind of gas we have at standard temperature and pressure, which is 0 Celsius or 273 Kelvin, and 1 atmosphere or 760 millimeters of mercury, or 101.325 kilopascals, 1 mole of gas at standard temperature and pressure always takes up 22.4 liters of space. That's our standard molar volume. 1 mole of gas at STP is 22.4. Now that we've talked about the fact that standard molar volume, or the mole of gas at STP, always takes up 22.4 liters of volume, what we can do is take a step back and realize we now have a molar amount, a temperature, a pressure, and a volume that are all related to each other. 1 mole of gas at 0 Celsius or 273 Kelvin, 1 atmosphere, 760 millimeters of mercury, 101.325 kPa. These three values are all equal to each other. They're all the same pressure, just different units, and 22.4 liters. Guys and gals, that is 1 mole at STP, standard temperature, standard pressure is 22.4 liters. We're going to be using that set of data right there called standard conditions. 1 mole at STP is 22.4 liters. We're going to be using that with the PV over NT relationship that we talked about a couple slides back to derive the ideal gas law equation and to find the ideal gas law constant, or the universal gas constant as it's sometimes called in video 2. We covered a good bit of information in this video, but please make sure that if there's anything you missed, go back. So if you need to go back and review it before you take the test at the end of the week, please feel free to do so. If you feel confident with this, go ahead and move on to video 2, which is where I'll start walking you through how we came up with the ideal gas law equation and the ideal gas law constant